Here we're going to derive the formula for centripetal acceleration, the infamous v squared over r, using just the definition of acceleration. So what we're going to do is just start out with a circle, and we're going to put a point P at the top of the circle. And what we're going to actually find is the acceleration at point P, and it is a vector, and here we're in 2 dimensions, so we really need to include the fact that it's a vector, is equal to just the change in velocity, which is a vector, divided by the time that it takes. That's the only definition we're going to use. And what we're going to do is take a point that's right before P over here, and another point right over here just after P, and we're going to find the velocity at this point and the velocity at that point, and find what is their change. And the change is only going to be a change in direction, because we are going to assume we are in uniform circular motion, which means the magnitude of the velocity is constant. The only thing that's going to change is the direction. This vector has the same length as that vector. However, they're pointing in different directions. And that change in direction is what's going to give rise to an acceleration. Now, just to make the derivation a little cleaner, we're going to make a slightly neater plot right here. And what we want to do is find out what is the acceleration at point P, which is a vector, and that will equal the change in velocity, which will be the velocity at the end, right here, right after point P, minus the velocity right before. So that'll be the velocity at point B minus the velocity at point A divided by the time it takes to go from A to B. Now, remember that the magnitude of the velocity at point A is equal to the magnitude of the velocity at point B, and just for simplicity, I'm just going to call that V. And that will be the same throughout. Now, this right here, this formula, is actually the average acceleration over an extended time. I'm actually going to want to take the limit as this delta t goes to 0. Now, I'm picking my point A and B to be the same angle theta before and after point P. So as delta t goes to 0, theta will also go to 0. So my limit will actually be, I'll let point A right here go to be right before point P, and I'll have my point B go right after. And that will be my limit as delta t goes to 0. Now, once we see this, we have to basically calculate the acceleration, and the acceleration is a vector. And probably the easiest way to do this is to break the velocities into their x and y components. To do that, I'm going to need to know what is the angle between each one of these vectors and the x-axis, which means I need to do a little bit of geometry. Now, right here I've given you the answer, namely that this angle right here is going to turn out to be the same angle as this angle down here. But let's prove that. So what I'm going to do is look at just the simplified geometry. So all I have right here, this is the radius vector that goes from the center of the circle out to point A. And this right here is the velocity vector. And the angle we want to find is this angle right here, which I will simply call phi, using the Greek letter. And what I want to do is find out what is phi. Now, this is the velocity vector right here, and this is the radius vector right here, and the velocity is always tangent to the path, which is the circle, and the tangent to the circle is always perpendicular to the radius, which means this angle right here has to be a right angle. Now, a little bit of geometry says that this angle right here is the complement of theta because this is a right angle. That has to be a right angle because this is the x-axis, this is parallel to the x-axis, and this is the y-axis, and the x and the y-axis are always at right angles to each other. So this triangle right here highlight in red, this triangle right here is a right triangle, which means this angle right here is the complement of theta. So this angle is 90 minus theta. However, this angle right here, which I could call, I don't know, alpha, using Greek letters again, just because the Greek alphabet's fun. This angle alpha and the angle phi that I want themselves, remember, form a right angle. So therefore, phi plus alpha must be 90 degrees. But I know what alpha is. That is 90 minus theta. So therefore, we have phi plus 90 minus theta must equal 90 degrees. I have 90 on both sides of the equation. They cancel out. I can bring the theta over to the other side, and lo and behold, I find that theta and phi are the same angle. So theta and phi are equal. I could also argue that, using a little same reasoning, but basically that this right here is the complement of theta, and this is the complement of theta, and the complement of theta is theta. But just to say that the complement of theta is theta, because here I have 90 minus 90, which is 0, and minus theta is theta. So this angle that I'm looking for is the same angle as this one right here, which is what I want. So now that we have the geometry done, we have that for A right here, this is the geometry we have. Let's just get rid of that circle right there. And for A, the velocity in the x direction is just going to equal v cosine theta. And the velocity in the y direction is just going to be v sine theta. That's the geometry for A. The geometry for B is exactly the same. And the only difference is we have the velocity in the x direction is the same. It's v cosine theta. But notice this is angled down, so this vector is pointing downward, so v sub y is minus v sine theta. And that's going to turn out to be the key, because notice the magnitudes of the components are the same. The only difference here is this sign. This has a minus sign, this one does not. That's our change in direction. Now what we need to do is just calculate the two components separately. So here we're going to do our calculation. I'm going to break it in half. And over here we're going to calculate the acceleration in the x direction at point P. Put a P right here. And that will simply equal the change in the x component, which will be v bx minus v ax divided by the time it takes to go from A to B. But we already found out, we go back here, that v sub x for A is v cosine theta, and it's the same thing at point B, so therefore this is just going to equal v cosine theta minus v cosine theta divided by delta t, which means it's 0. There is no acceleration in the x direction. All the acceleration will be in the y direction at point P. And that will equal the exact same formula, just with y. So it's v by minus v ax minus v ay divided by delta t. Now, these two components have the same magnitude, but different directions. Remember, one of them was v sine theta right here without a minus sign, and this one had a minus sign. So at B, we have a minus sign. So when we write this down, this will equal minus v sine theta, that was B, minus v sine theta, that was A. Put a plus sign in there because that one did not have a negative sign in front of it. All of that divided by delta t. This does not cancel out to 0. This will actually equal a minus 2 sine theta times v, all that divided by delta t. Now that is not 0. Now we need to simplify this expression, because in a sense we're done. It's just that the expression is not exactly the form we want it to be. To simplify this, I want to find out how long does it take to go from point A to point B? What is this delta t? So let's look back at our diagram here. It's getting a little messy, so what I'm going to do is edit and get rid of all the ink. Now, what we have is how long does it take this object in uniform circular motion to go from point A to point B? How much time does that take? Well, that time will equal the distance it travels, which I'll just call L, and that's the distance along this arc right here, divided by its constant speed. Remember, it's moving at a uniform rate the entire time. Now, what is L? Well, L will just equal the radius of the circle times this angle right here. And that angle is just 2 theta. That's the same logic that tells me that the circumference of the circle is 2 pi, which is this angle, times the radius. And this is just a fraction of that. So L is just r times 2 theta, which is the angle subtended by the arc L. So I can take and plug that into here, and I get that the time is just 2 theta r divided by the constant speed v. So that's my time. I can now take and plug that into here, and we get that this is equal to, again, my minus. I'm going to take the v out, and then multiply this by 2 sine theta, factoring out the geometry part. Then over here I have delta t, which was, go back here, remember it was 2 theta r over v. And again, I'm going to take the geometry part out, so it's r over v times 2 theta. So this is r over v and 2 theta. Now we notice the 2's cancel out, and what we have right here is my physics part, which is v divided by r over v. That's just, I guess I'll have some more room, minus v squared over r times the geometry part, and all I'm left with is the sine of the angle divided by the angle. This I want to evaluate as theta goes to 0. Notice that's a limit. Now, in calculus, one can show this rigorously. Here I'm just going to argue that if I actually plot it out, I can see what that limit's going to be. So what I'm evaluating right here is the ratio of the sine of x over x. This is x in radians. Remember, I used x in radians when I did this geometry back here. This right here, this angle had to be in radians. Because notice, this is the angle. This is 360, oops, 360 degrees in radians. So I was using radians all along. Oops, there. So this is x in radians, and this right here is the sine of x over x. Notice these are small angles. We're starting with a small angle. And notice the ratio here is 0.9982 at the bottom. And it approaches 1 as the x goes to 0. So the limit of that is just 1. So that unfortunately my links aren't working, but this right here is just 1. So that tells me that the acceleration in the y direction is just minus v squared over r. Now that's not quite what we were looking for. So now what we need to identify is what exactly does this mean? And here I've drawn this geometrically as to what the acceleration means. The acceleration has, if I write it in vector form, acceleration at p is equal to 0 times I minus v squared over r times j. Because this is the x component right here, which was 0, and this is the y component, which was negative. Now if I draw that right here, the y component simply tells me it is pointing downward towards the origin. So it tells me that the acceleration has a magnitude of v squared over r and a direction which is downward. That is the direction if I happen to pick the point P at the top of the circle. I picked that for convenience, mainly so that my x and y axis will be horizontal and vertical. And the top of the circle is the easiest place to draw things. I didn't have to do that. What would happen if, in fact, again, we'll clear the ink from the page, I chose not to do that? Instead, I could have picked my P at any point, over here. My axis would be cocked at a strange angle, but I do the exact same problem, and again I would find the acceleration would be a minus y pointing towards the center of the circle. And I could turn this circle any way I want. And again, I'd find the center of the circle wasn't where I originally drew it, but that's okay. I'd find the acceleration points towards the center of the circle, no matter how I turn the circle around. So what we're finding is that the centripetal acceleration has a magnitude of v squared over r. This is the magnitude. And the direction is to the center. That's what the minus sign meant. So now we have the magnitude and direction of the centripetal acceleration in a uniform circular motion.